here we are talking about computational techniques to solve linear equations. So what I am going to do in this particular module is consider linear equations and linear systems and go over some of the methods to solve these linear equations. So we will first go and motivate ourselves what linear equations are. Before doing that, we will just talk about some of the prerequisites. I will assume some familiarity with the concepts of linear algebra, vectors and matrices. For example, I will assume that you know how to multiply two matrices, or what vectors are, what are the addition rules for the vectors and matrices, what are the multiplication by scalar rules for vectors and matrices, and all these things I am going to assume. We will just do a quick recap of that, but it is just going to be a few minutes of a short recap just to orient ourselves with the terminology that I will use in this particular module. If you are not familiar, or if you are a little bit rusty with these concepts, then I would request you to please review your +2 syllabus and your first year undergraduate syllabus. Specifically look at the linear algebra, vectors and matrices parts of those courses. Okay. So those are essentially going to be prerequisites for this course. What I will do in the next few minutes is just go over some of these concepts. What do we mean by scalars, vectors, what are matrices and so on. Okay. So a quick recap. So the question, what is a scalar? A single real number in this particular case is what I define as a scalar. So an example over here is a equal to 1.23. This is going to be a scalar. So it is just a single number, and we are restricting ourselves only to real number. A vector on the other hand can be considered as an ordered set of scalars. What do we mean is that it is not just one single number, but several numbers. In this particular case we have two scalars, number 2 is a scalar, number 3 itself is a scalar, and an order set of these two scalars is a vector. This vector we have represented as x over here. Okay. Now the number of scalars that go in representing a vector is typically gives the dimension of that vector. For example, in this particular case the vector is 2 dimensional. Now these vectors can either be row vectors or column vectors. This particular case we have basically 2 rows and a single column. The other way of representing this is x equal to 2 comma 3, which basically means that it is going to be a vector in a single row, that is a row vector. Okay. However, consistently when we talk about vectors in this particular module, what we would mean is that the vector consists of n rows and one single column. So this is how we will typically represent a vector. So if, for example, if a vector is 5 dimensional, there will be 5 numbers stacked on top of each other. So 1, 2, 3, 4, 5, that would be essentially a 5 dimensional vector in our case, and it will not be in a horizontal direction, the vector that we represent. Okay. So that is what terminology we will follow for this particular module. Now another concept associated with vector is the length of the vector, or basically a distance of the vector, you can call that, and the second property is going to be the directionality of the vector. Okay. So it has both a length associated with it and a direction associated with it. Geometric interpretation of a vector is, you can consider a vector as either a point in an n dimensional subspace, space, sorry. So this particular point is going to be a vector that is 2 comma 3. That means that the dimension in the first direction is going to be 2, and the dimension in the distance in the second direction is going to be equal to 3. Okay. So one way to look at it is a vector is going to be a point that in an n dimensional space, but a more appropriate way or a more common way to look at it is it is a point that is connected by an arrow or a line to the origin. So when we say a vector 2, 3, what image it typically conjures up is basically of a line going from the origin to a point 2 comma 3, and as shown by this light green line over here. Okay. So that is going to be the geometric interpretation. in this particular example, the dimension of this vector is 2 and we represent this as x is an element of the R2 space, R representing real numbers and 2 is represents the dimension of that particular space. Okay. And just a moment back I said that we consider that the vector has a length or a size of the vector. So, instead of talking about length, we will actually talk about the norm of a vector, and the length of a vector is nothing but what is known as a Euclidean norm of a vector. For example, in this particular case, the length of this vector is going to be equal to 2 squared plus 3 squared square root of that number. So, the length of this vector is going to be square root of 4 plus 9 or square root of 13, and then there are several linear operations that we can do on this particular matrix, and that is addition, subtraction, scalar multiplication. These are the various linear operations that can be done on a matrix or bunch of matrices, and we should be familiar with the rules of addition and subtraction. You can add for addition of two different matrices, the dimensions have to be the same. That means you can add a 3 by 2 matrix to another 3 by 2 matrix, you cannot add a 3 by 2 matrix to a 2 by 2 matrix, for example. Same thing with subtraction. Now you can multiply any matrix of any size with a scalar, and so if we were to consider alpha A, alpha is going to multiply each element of the matrix A. Okay. Then there are matrix multiplication rules. Again, I will not go into the matrix multiplication rules, but for the two matrices to be, for us to be able to multiply two matrices, those matrices have to be commutative. That means that the number of columns of the first matrix should be equal to the number of rows of the second matrix. So, in this particular case, we cannot multiply A multiplied by A because it is a 3 by 2 matrix. So, when we cannot multiply a 3 by 2 matrix to another 3 by 2 matrix, but we can multiply A with A transpose, in which case it is going to be a 3 by 2 matrix multiplied by a 2 by 3 matrix, and the result is going to be a 3 by 3 matrix. Okay. So, these are again the matrix rules, multiplication rules, and you should be familiar with the matrix multiplication rules. If not, it is a good idea at this stage to stop this video and perhaps go and revise some of the matrix multiplication rules. And the final thing is going to be that I will assume that some familiarity with is eigenvalues and eigenvectors. We will go over what we mean by eigenvalues and eigenvectors, but we will not necessarily discuss how to get eigenvalues and eigenvectors and so on and so forth. That is what I will assume you already know based on your previous +2 syllabus and your first year undergraduate syllabus. Okay. So, this really is a quick recap, and what we mean by a linear equation is an equation of this type. For example, 3x plus 4y plus 7z plus 2w equal to 17. So, x, y, z and w are the various variables. So, since I have used a notation of this form, this notation will represent a scalar and a bold-faced notation will represent a vector. So, in this particular case we have 4 variables x, y, z and w. There are 4 coefficients 3, 4, 7 and 2. So, this represents the left hand side of the equation and the right hand side of this equation is 17. Okay. So, this is a linear equation that we have. Now, if we want to try to solve this linear equation, there are 4 unknowns. So, that we need at least 4 equations in order to get a unique solution for this particular case. Though if we have 4 equations, that does not guarantee a unique solution, or that does not even guarantee occurrence of a solution, and based on the past knowledge, I think most of us over here will be familiar with the fact that for n equations in n unknowns to have a unique solution, the rank of a matrix has to be equal to n. Now, what that means and what exactly we mean by rank of the matrix should be n, where exactly does the statement come from, those things we are going to discuss in the next few minutes. Okay. So, this was overall a recap of the things that we have done so far.